Swayam Prabha. Digital India. Educated India.
Welcome to the class. Topic of discussion of now is condensers. We had seen turbines, we had seen boiler, and then we had also seen the psychrometry, which is necessary for understanding the processes which are very much going to happen in the condenser. Okay, so let us see how condenser works in a brief. So condenser, it has following functions. First function is to reduce pressure at turbine exhaust or to keep low pressure at the turbine exhaust. We know that if we keep lower and lower pressure at the turbine exhaust, then more and more expansion can take place for given turbine inlet condition, and that will increase the turbine work output. So condenser's job is to condense at as much low pressure as it can, such that we can have higher work output from the turbine. Second function of the condenser is to reduce or recover high quality feed water to recover high quality feed water from condensate so as to supply to the pump. Okay, so these are the two major functions of condenser. Now we will see types of condenser. There are basically two types of condensers. One is direct contact type condenser. Here the water and the cooling water and the condensate or the steam at the exhaust of the turbine will be in direct contact with each other, and then the steam will get condensed in the presence of the cooling water, and then the resultant stream will be then used for further processing. So this is direct contact type condenser. And there is one more, which is surface condenser. Here the cooling water and the steam will not come in contact with each other, then there will be heat transfer. So this type of condenser is a heat exchanger, where mostly it is a shell and tube type heat exchanger, where heat will get transferred through certain medium between the steam and the cooling water. So let us see some sketches for the types of condenser. So first is direct contact type heat condenser, and this condenser looks like this, where So this is state 1 where we are getting turbine exhaust. So this is steam. Then this is the cooling water at state 3, it is sprayed in the air, and then this is state 2 which is the condensate, and then this condensate will be pumped and some will be again circulated in the cooling tower. So here in the cooling tower, this water which is a cooling water will be cooled and then it will be passed into the condenser where it is directly coming in contact with the exhaust steam, and then rest will go to the plant. So this is how this is state 4. So now if we try to write down equations, then we will have m dot 1 which is mass flow rate of the steam coming from the turbine exhaust into H1, its enthalpy is equal to m dot plus m dot 3 into H3 gives us m dot 2 into H2. So we have m dot 1 into H1 plus m dot 3 into H3 is equal to m dot 1 plus m dot 3 into H2. So this is from the fact that since we have m dot 1 plus m dot 3 is equal to m dot 2 which is mass conservation, and we are working here on energy conservation. So we can have m dot 1 H1 plus m dot 3 H3 is equal to m dot 2 H2 plus m dot 3 H2. So we can have m dot 3 into H3 minus we will have m dot 1 into H1 minus H2 m dot 1 into H1 minus H2 into m dot 3 is equal to m dot 1 into H1 minus H2 equal to m dot 3 into H2 minus H3. So we will have m dot 3 upon m dot 1 is equal to H1 minus H2 divided by H2 minus H3. So we would know this enthalpy difference, which is the difference at the inlet and at the outlet of the condenser, and then we can know what is the enthalpy difference for the cooling water so as to condense the exhaust stream. Then upon that we can find out the ratio of mass flow rates, and then that will give us amount of cooling water to be circulated. So this is how we can work. Now this is a direct contact type cooling, that is direct contact type condenser. Now next we can have similar way one more condenser, again in direct contact type, which is called as barometric condenser. This condenser again has direct contact between the steam and the cooling water, but here this mixture is passed through a long tail, and that tail will put this mixture into a hot well. So this is tail, and then this is tail pipe, and this is hot well, and from here we are getting cooling water, and then this cooling water will splash over the baffles. So these are called as baffles, and then we will have steam from the turbine, and then there will be some non-condensate. This is non-condensate. So this cooling water would come out, it will get splashed, and then it would mix with the steam, and then steam will get condensed in this process, and then it will mixture will come down. This is mixture, it will come down and get settled in the well. This height of the tailpipe is very much required, such that we will have rise in the pressure of the mixture. So the mixture will come at low pressure, and in the process of condensation and passing through the tailpipe, after condensation, passing through the tailpipe, it will rise its pressure to the atmospheric pressure. But this barometric condenser needs a long pipe for the pressure building. Instead of that, sometimes a diffuser kind of condenser is also used, where we will have this as the hot well, and this is the diffuser. Then there will be baffles, are also called as cascades. This is turbine exhaust. This is cooling water. And then these are called as cascades. Here this mixture, while passing through the diffuser, rise its pressure. So this is how we will have a diffuser type of condenser, which will reduce the height of the tail. And then we will have surface condenser, and that surface condenser will not have direct contact of the steam and the water, and then we will have the process of condensation without contact. So here these are the shell and tube type of heat exchangers, where we can sketch a typical non-contact type or surface condenser. Here we are having exhaust of turbine. This we will have cooling water in, this is cooling water out, and in this phase this is not the mixture, only steam will get condensed and then it will get settled into the hot well. This is a typical surface condenser, which is a heat exchanger, where we will have the water pipes which have the ability to transfer the heat from the steam to the water, and this is similar to what we have seen in case of boilers. Having said this, we will move now towards the cooling tower. We have seen that cooling tower is a part of condenser, and this cooling tower is very much required to cool the cooling water. Cooling water, upon in contact or after having heat transferred from the steam, will get heated, and that cooling water needs to be recirculated into the condenser. So we have to remove the heat from the cooling water, and that removal of the heat will be taken in the cooling tower, where we will use atmospheric air to cool the water in the cooling tower. And then typical sketch of cooling tower is like this, where we will have so hot water will come into the cooling tower, and then that would get sprayed on the over the packings, and then this will get splashed and come in contact with the air, which is circulated through a circulating fan, which will come from the bottom and then will get heated, and then it will get removed from the top. So in this process water will get cooled, and then this is the cold water out. This is a typical sketch of the cooling tower. So here we are cooling the cooling water, which is not part of the Rankine cycle. Rankine cycle is having water which will get evaporated in the boiler, then expanded in the turbine and condensed in the condenser. That water which is getting condensed into the condenser is having its heat transferred to this cold water, and this cold water in this process will become hot. So the same water which is used in the condenser to extract the heat from the steam is now hot. After extraction of heat, this water should again be passed to the condenser. So for that it is cooled in the cooling tower with the atmospheric air. Now there are certain things which we should know, that the minimum temperature to which water can be cooled from TC1, which is TC1 cooling water temperature. This is TC2 to TC2 is the adiabatic saturation temperature or wet bulb temperature of air. So this point is very much to understand that the air which is coming in is already humid. It will have certain phi 1, and then this phi 1 of air, after having mixing or after having mixed and transferred heat from the water, will have certain phi 2. So in this process we are cooling the water, but we cannot cool the water if phi 2 becomes 1. So this is wet bulb temperature. So this point is important, that at this wet bulb temperature we are having 100% relative humidity. So we cannot cool beyond this. So there are certain concepts for the cooling tower, and first concept is called as approach. Approach of cooling tower is called as A, and that is equal to TC2 minus TWB. This is the temperature of the cooling water at the exhaust of the cooling tower after the process of cooling, minus TWB, which is wet bulb temperature corresponding to phi is equal to 1. This is called as approach of cooling tower. Second is called as the range of cooling tower, and this range is defined as R. This is equal to TC1 minus TC2. So the actual cooling, what cooling tower does from TC1 temperature to TC2 temperature, is called as range of cooling tower. Then there is third concept, which is called as efficiency, cooling efficiency, and then this is eta, and this is equal to actual cooling divided by maximum possible cooling. So efficiency of cooling tower is actual cooling is TC1 minus TC2, which is range, and maximum possible is TC1 minus TWB. So that is wet bulb temperature. So this is what the efficiency of cooling for a cooling tower. Now we can use the concepts of psychrometry to understand the different heat transfers and different masses of the airs and the humid air, and also for the water vapor. So we can use these concepts for better understanding of the cooling towers and also for the condensers. Thank you.